Good morning, everyone. Welcome to our last seminar for the fall ECE Colloquium seminar series. It's my pleasure to introduce today's speaker, Dr. Kevin Barker from Pacific Northwest National Lab, PNNL. Dr. Barker has been the group lead and director for the high performance computing group for over 16 years. He has done work across the entire full stack of the HPC, from network architecture all the way to the software hardware co-design that we're going to hear about those today, I believe. And he's been the PI for several DOE grants. So with that, please virtually welcome Dr. Barker, and you can take it away, Doctor.
All right, thank you so much. Thank you for that introduction, and thank you for the invitation. I'm sorry I'm not there in person. I actually am now on the East Coast. PNNL has kind of opened up remote work for the laboratory, which is new for us. So I actually took the opportunity to move to North Carolina. So I was hoping to combine a trip to Seattle with a trip back to the Tri-Cities in Washington, and that didn't pan out. So I appreciate your flexibility and having a remote seminar, and I'm looking forward to it. And hopefully in the future, maybe one day I can actually come pay a visit and meet some folks in person. That would be great. But yeah, like what was just mentioned, I'm going to talk a bit today about co-design, and particularly a co-design initiative that we have at PNNL. We're now in the 5th year of, called the Data Model Convergence Initiative. And so really what the aim of this initiative is to develop co-design methodologies to support what we call converged scientific applications. And I'll talk a little bit more about that as well. So this will be a fairly high level talk. I won't get into nitty gritty performance graphs or anything like that. But if anyone has any questions, please just let me know. And if you would like more information as well, follow up with me afterwards. I can leave my email address, and I'd be happy to point you to some resources and some other folks who are also helping with this project. So I've served as the chief scientist for the DMC initiative for the past couple of years. Like I said, it's a 5-year program. My title slide has some of the other folks who are in the team. It's led by Jim Ang, who has been with PNNL now for about 5 years. He was at Sandia National Labs for 28 years before that. And then we have a couple thrust leads here, Draguna Vrabier and Gochin Kestor. So I'll be covering some of their work as well. If I can figure out how to advance my slides. There we go. So just a quick outline of what I'll be talking about. I'm going to give a very brief overview of PNNL for folks that don't know about the laboratory, just to share a bit about that, and then get right into the Data Model Convergence Initiative, some of our goals and challenges, as well as motivation for some of the research that we're doing within the initiative in a couple thrust areas that we call converged applications and heterogeneous computing. And then at the very end, I'll touch a little bit about advanced architectures and test beds, which touches on another program that I have led at the lab for the past 5 years or so, called the Center for Advanced Technology Evaluation. And I'll talk about that just briefly at the end. So this is kind of an aerial shot of the Pacific Northwest National Lab campus. We are located in the Tri-Cities in Washington State, so not too far from Oregon or Idaho. We're kind of down in the southwestern or southeastern corner, excuse me. And this picture is already out of date. So you can see there's a couple of areas of construction, one called the Energy Sciences Center and one called Grid Storage Launchpad. The Energy Sciences Center is actually open and functioning, and that's a really nice facility that houses a lot of our chemistry and catalysis folks. We're a lab of about 6,000 people. I think we'll have 6,000 people here by another month or two. And we span a lot of areas of science and engineering. So, you know, computer science, certainly, but we're really known for chemistry, for biology and earth system sciences, molecular sciences, and national security. And we do quite a lot with the power grid. So, you know, complex engineered systems and power grid in particular. So we have quite a depth, or quite a range, I should say, of expertise at the laboratory. So I've, as mentioned, I lead the high performance computing group. If you count our postdocs and our interns at any given point in time, we're about 60 people. And we do research all across the hardware software stack, from applications, tensor algebra libraries, down to compilers, runtime systems, and architecture, design exploration, and high-level synthesis tool chains. So we have quite a few teams within the group and quite a range of expertise. So really, what do we say when we talk about hardware software co-design? This is a term that's been around for quite a long time at this point, but we're really looking at how can we design hardware and software in concert with one another in order to achieve, or in order to maximize some metric of interest, whether that's performance or power efficiency, or perhaps even area or resilience or things like that. And co-design has been around for a long time, at least the term. Prior to me joining PNNL, I was at Los Alamos National Laboratory about the time we were standing up the Roadrunner system, which was the first petascale computer, general purpose petascale computer, and hardware software co-design was a big topic area at that point too. The thing about co-design in that context always was the hardware was already kind of a fixed point. You've got to do hardware design and tape out years in advance of deployment in any sort of system. So co-design, hardware software co-design really kind of morphed into software porting and optimization for a particular architecture, because the hardware was not something that you could really adjust in any sort of reasonable time frame. However, that's starting to change, and I'll talk about some of the technologies that we employ, like coarse-grained reconfigurable arrays and even FPGAs, and how we can really bring co-design or hardware into the co-design loop. So we also look at future HPC architectures, maybe things that are a little bit more far forward-looking and disruptive, like neuromorphic or quantum non-von Neumann architectures, things like that. And really, we look at how can these technologies impact future leadership class computing systems. PNNL is not a DOE leadership facility. We don't have an exascale computer at PNNL like Argonne or Oak Ridge or Livermore will. But that gives us actually some advantages, I think, because we can be kind of agile. We can be a little bit more agile, a little bit more nimble. We're not tied to these industry partner vendor roadmaps like some of the large facility labs are. And so that gives us a little bit more freedom to do some more blue sky exploration, I think. On the other side is software. So we don't just talk about hardware, we also talk about software. And really, in this talk, I'll be talking about convergence of different software paradigms, different high-performance computing paradigms, from scientific simulation, which is kind of the more traditional bread and butter of HPC, numerical simulation, to now AI and ML and data analytics, and how these things can come together to integrate to define a new type of scientific computing, where these different pillars of computing are merged, or what we call converged. So when you see me talk about converged applications, I'm really talking about this junction or this joining of physical simulation, numerical simulation with AI, ML, and data analytics in a tightly integrated way. So not just a sequential workflow of different stages where you might pass data, through a file system or through some other means, but really how do we bring them into tight integration so that you might have AI, ML, and numerical simulation within a loop, or within the inner loop of an application, or perhaps you're using AI, ML to do decision support for experimental steering or something like that. So that's kind of the high level definition of what I mean by convergence in this talk anyway. So, that's kind of the introduction of PNNL and the HPC group. And now I'll dive a little bit more into DMC, or the Data Model Convergence Initiative, which is really kind of the meat of this talk. And so what is an initiative? Perhaps I better explain that up front. So in the DOE laboratory nomenclature, or at least PNNL's nomenclature, an initiative is an internally laboratory funded portfolio of projects that has about a 5-year time span. So an initiative will last 5 years. It will be a portfolio of projects. Each one of those projects is limited to a 36-month time frame. And so you kind of have some projects ending and starting throughout the initiative's lifespan. DMC is an initiative that we started about 4 years ago. So we're actually getting towards the end of DMC. And the idea behind the initiatives is we want to be able to support lab level priorities in science writ large. So not just computing, but broad science. And one of the laboratory's high level priorities is something that they call automated reasoning or machine reasoning. So the far-reaching vision or the far future vision is that, through automated methods, computing, AI, ML, the evolution of AI and ML techniques, we might be able to have what is referred to as an automated laboratory, where we can have experimental design, experimental steering done primarily by machine. Of course, this is kind of a far-reaching vision. We have a long way to go before we can get there. But that's kind of the end goal anyway. And the idea is to enable, transformative science, right? It always comes back to the science domains and how can computing support these transformational science opportunities? How can we accelerate scientific discovery through advanced computing techniques and concepts? And so that's really kind of the vision behind why DMC was started. And really, DMC kind of began with the recognition, as many people across the computing industry have had. This is not a original thought by any stretch, but the recognition that Moore's law is ending, right? So we can't ride the wave of technology scaling anymore to achieve the computing performance requirements that are going to enable this vision. So we have to have a different approach, right? We can't just wait for the next generation of hardware technologies. We have to think something differently. And so the goal behind DMC, or the impetus behind the DMC initiative, is developing heterogeneous and reconfigurable computing technologies together with the entire software stack that would be needed to support such things, that will drive kind of the 1000x performance per decade performance cadence that we've gotten used to with technology scaling resulting from Moore's law. So, over 20 years, could we lay the groundwork today that in the next 20 years might lead to 1 million times performance improvement? That's something that it sounds amazing, right? You could have 1 million times performance improvement in 2 decades, but that's what we've seen in the previous 2 decades. We went from terascale to exascale in roughly 20 years. So how do we continue that pace of performance improvement for the next 20 years, given that, even now Moore's law is starting to impact GPU performance. So that's the lofty vision at any rate. So, how are things done now, and what is the problem with how things are done now? What does DMC hope to be able to perhaps address or potentially correct? Well, we have AI, ML, we have HPC, we have graph analytics and data analytics, but they exist in kind of independent silos, discrete computational paradigms, you might say. And that extends from the programming languages that we might use, to the programming models that are used, to the system software that's used, the libraries and tools, in some cases, even the computer architectures that are used. And so this leads to a lot of problems if you have this vision of converged applications, right? If I want to merge or converge HPC with AI, ML, HPC, that's been the domain historically of languages like Fortran or C or C++. We're seeing some new things now like Rust and some other things, but those are largely distinct from Python and some of these other tools that we see in the AI ML space, and they don't play that well together, right? There's not a nice clean way to integrate those two things. And so we want to be able to think from DMC, what is required in terms of tools, programming languages, perhaps, programming models, perhaps, system software, certainly, even tools like compilers and things like that. How can we develop new tools, new techniques to help integrate these different computing paradigms and end up with a picture that looks more like this, right? Where we still have graph analytics, AI, ML, high performance computing, but those now are supported by a unified software stack or software hardware stack, I should say. So, you know, in the bottom, this kind of pyramid shape on this slide, where we have at the top application domains. Those application domains are where the convergence is occurring, but then those are supported by a software stack and a hardware architecture. So this has kind of been the driving vision for DMC for the past 4 to 5 years. And, you know, how do we go about achieving such a thing? So, you know, for the rest of the talk, basically, I'm going to talk a bit in more depth or a little bit more detail about DMC's approach to achieving this kind of vision and some of the groundwork that we've laid up until this point in terms of projects that have been under the DMC portfolio and how those support different aspects of this vision of a unified software stack. So hopefully that is a fairly clear picture, and I was able to define what we're trying to do and what the gaps are from where we are today to where we're trying to get. So hopefully that made a little bit of sense. So what are the goals and challenges then that we saw right off the bat, right? Certainly seamlessly integrating scientific computing, HPC, and data analytics is a challenge, and for many of the reasons that I've already kind of discussed, that was a problem. But we also wanted to use DMC as an opportunity to extend computing beyond where it is today in order to achieve orders of magnitude improvement in efficiency and performance to enable kind of revolutionary new scientific methods, scientific processes. So if we freed the domain experts or the scientific computing experts from the architectural constraints in the computing systems that they use today, the constraints presented by those computing systems, if those were somehow mitigated, if not eliminated, what would that do in terms of freeing up opportunities for algorithmic development or application development or new types of applications and so forth? And so really it was this transformative science that really underpins all the rest of what we want to do. So we settled on this idea of co-design, right? Which I've mentioned previously in this talk already. Co-design, where we can design the hardware and software together. Now that can potentially lead to extreme specialization, right? You could design an ASIC that supports a single application or a single algorithm, but that's not really what we wanted to do. We can think about the MD Great machine as perhaps an example of that, where an architecture was designed exclusively for molecular dynamics in the service of drug discovery or something like that. We wanted to have a broader set of mission drivers and be able to support a broader cross-section of the scientific computing community. And so, we wanted to have something that in our outcomes was a little bit more far-reaching than perhaps an ASIC, a particular ASIC, or something like that. We also had mission drivers that aren't strictly science. We're a scientific laboratory. But we also, as I mentioned at the top, do a lot with the power grid. So, control of complex engineered systems was also a driver for us. And in particular, in the early days, that was a major driver for us. So, if we had a distributed computing infrastructure, perhaps edge computing devices combined with sensors and actuators, combined with larger scale back-end computing facilities, what types of computing is necessary to achieve that kind of vision? How would we do that under extreme latency constraints, right? Where perhaps shipping data to the cloud and getting something back, or shipping data to an HPC facility takes too long. So we need edge computing devices that can operate or provide at least initial processing under extreme latency constraints, perhaps combined with power constraints, right? So it becomes a challenging environment to try to develop systems for. And of course, we want to accelerate scientific discovery across biology, chemistry, material science and discovery, energy application domains, and so forth. So it's a broad challenge, I think, that DMC was really initially conceived to address. And I think, over the course of the past 4 to 5 years, we've achieved some success in that. But it is certainly a tall order, and it's something that is ongoing. So, the idea of a DMC-like initiative is to build a capability, or at least the foundation of a capability that can then be used to achieve perhaps additional programmatic funds that might come from a government sponsor or somewhere else. And so, it's that initial groundwork, ground laying that we tried to do here with DMC. And I'll dive in a little bit to show you some of our success rates to date. And as always, if there are questions, please speak up at any time, and I'm happy to stop. If you see something interesting on a slide that you want to know more about, I'm happy to dive in. So, what are the 2 approaches, that we used within DMC? The first is convergence, and the second is co-design. And you're going to hear those words a whole lot in this talk, but convergence and co-design really is the bread and butter of what DMC is. And so, if we go back very quickly to this slide, you see the 4 elements of the pyramid shape here, from application domains to algorithms and methods to software stack, and finally hardware at the bottom. When it came time to actually do the project management and how we lay out the DMC project portfolio, we combined some of those into 2 particular elements, 2 thrust areas. The first is converged applications. And so the challenge problem, of course, is how do we converge physical science with data science applications? And, in both cases, in the case of convergence here, there are technical challenges, and I think there are also somewhat, for lack of a better term, cultural challenges with how we do this, because it's a new way of thinking about approaching the particular scientific challenge problems. And it's not something that the domain experts had thought as much about before DMC started, 4 or 5 years ago. Now it's much more common where, domain scientists are thinking about how can AI ML help with their particular challenge problems. And it's something also that our sponsors have largely recognized as being important. And so we see calls coming from our particular government sponsors that are looking at how can we use AI to accelerate some element of domain science. But 5 years ago, that wasn't quite as common. So this was something that DMC was trying to lay the groundwork for. So So DMC software stack is designed to support converged workloads on heterogeneous computing platforms. We've really put a lot of emphasis on the compiler as the part of the software stack that can help us with that. And so we have a compiler project that's called Comet, the Comet Compiler Infrastructure Framework, that leverages a lot of the work coming out of the LLVM community and MLIR to achieve this. And I'll talk a little bit more about that. But also developing hardware designs that can make use of our expertise in design automation and high-level synthesis. And that's been really beneficial for us. I think that's a distinctive element that PNNL brings to this kind of problem, is that we have a very accomplished hardware, high-level synthesis and design team within our high-performance computing group. We work very closely with industry. And we also have stood up some advanced architecture test beds that can help realize some of the concepts that they're generating with their tools and actually try them out kind of in the field, so to speak. So I'll mention a bit more about that as well. The second approach, of course, is co-design. And co-design, we have drivers from both ends, so to speak. And this figure here kind of illustrates that, drivers from the top and from the bottom. Converged application challenge problems come out of domain science, and applications have requirements that must be met in order to ensure stability and performance. And so those requirements have to be satisfied by the underlying architecture and system software. But from the bottom, we also have hardware abstract machine models that can be used to communicate architecture design concepts to domain scientists. many of whom have not thought at all about what the architecture looks like in the machine. So this is definitely a learning process for everyone involved. Architects aren't used to thinking about full-blown applications. It's not something that can be simulated, and so it kind of, in many cases, exists outside of their purview. I always joke you can tell a lot about computer architects and computer scientists by how they define the word system. And if the word system is defined as a circuit versus someone else defines system as a supercomputer, then there's a bridge there that has to be built so that you can overcome that chasm. And so, in DMC, a lot of the early days were spent kind of thinking about vocabulary and converging on a language that we can all speak, that we all understand. And I think that's a lesson that we've learned that perhaps we underestimated in the early days, the effort required there. But it's been a great lesson. And I think, will bear fruit even well into the future. So, an effort definitely worth undertaking. In this figure, we kind of simplify the process a little bit. From converged applications, we have tools that we call proxy applications or proxy workflows. And this differs a little bit from the usage of the word proxy in the ECP community, in the exascale computing project community, where a proxy might be a kernel, a kernel that might capture a large fraction of the computation time of an application. They can distill that into a proxy application, which is self-contained and usually pretty small. Because of the convergence aspect of our applications, it's hard to do that because you might have proxy, or you might have important kernels that are in these different paradigms of computing, and how do you link them? And so we really spent some time developing proxy workflows, which are tightly integrated sets of kernels. They're composable, reconfigurable, adaptable to different kinds of input specifications, and so forth. And we distilled those into something called proxy applications or proxy workflows. From the architecture side, from the bottom here, we have architectural concepts that need to be communicated to algorithm developers. How can the algorithm use these architectural concepts? And to do that, we use something that we call abstract machine models. So these abstract machine models can be boxology, they can be PowerPoint, or they could be simulations, or they can exist at different levels of abstraction. But the goal is to communicate the capabilities of these architectural designs to the application developers so that they can understand, okay, if I rework my algorithm in this way, I can make use of this feature. Or I see that I need to have better, data tiling in this area where maybe we didn't have it before, or it has to conform to certain properties, or I can make use of this architecture without compressing my sparse data format, or something like that. So that's been a very powerful tool, and these are really for communication, again, across the different components of the entire stack. So I put this slide in here because a lot of time when I had given a similar talk in the past, some of the questions I would get would be, why do you even care about hardware research? Why are you worried about designing, different accelerators or things like that? And one misconception that, I always want to clear up from the beginning is that the goal in our research is not to define the next CPU or GPU. Right, we're not going to compete with NVIDIA. We're not going to compete with Intel. This is just not going to happen. We're a team of 20 people. They have 5,000 engineers working on this problem. Our vision for future computing platforms is really heterogeneous at the node level. So you might have a sea of processors or a collection of processors. You might have chiplets integrated into a silicon on package design, where we have chiplets integrated with compute cores from an x86 vendor or RISC-V or something along those lines. But we're not trying to replace any of those. We're trying to exist with them. And with new capabilities coming out of industry, I think this integration is actually becoming easier. We're seeing small scale manufacturing of chiplet designs that can be integrated on a package. And so some of these concepts that we're implementing with CGRAs or FPGAs, in the future, we may be able to actually implement in silicon in a tightly integrated way, perhaps at the package level. And so I think, that's exciting. Plus, we're making use of trends like reconfigurability for a couple of purposes. One is rapid prototyping. If we have a CGRA or something, we can test these architectural design concepts without having to tape out a chip and get something manufactured. And that's really been the bread and butter of FPGAs for quite a while. But we also use reconfigurability in and of itself. And I'll highlight that with a project that was in our portfolio called the compute flow architecture, where we actually make use of reconfigurability during runtime to partially reconfigure processors or computational substrates to do different tasks in a computational pipeline. And so, the reconfigurability itself is actually enabling some of these explorations that we're doing within DMC. So, finally, I think hardware software co-design is becoming feasible, and actually having hardware in the design loop is becoming feasible. We can test hardware design concepts rapidly. We can do them in-house. And this is something that we haven't been able to do very well anyway previously. And so I think this is an exciting time actually to be doing hardware research and hardware motivated research, even at the national labs where, normally we were on the outside looking into industry. But now we're working much more in conjunction with industry, and industry is recognizing that we have unique problems that perhaps, hardware that they're developing for commercial reasons doesn't address very cleanly. So I think this is actually a great time to be doing heterogeneous computing research. And heterogeneity, like I mentioned, is appearing in the commercial space now. P&L has ongoing collaborations with companies like Next Silicon, Samba Nova, GraphCore, who are developing these data flow reconfigurable architectures. We also have ongoing relationships with AMD and Xilinx, who are now the same company, where they've been developing reconfigurable computational substrates and integrating them with things like AI accelerators or hard ARM cores, in a single package. And I'll talk a bit about one of our testbed systems that we are testing all these concepts out on. That's really making use of some of those technologies. So that's a good thing as well. So this is just a slide that kind of breaks down our project portfolio. You can see we have a number of projects in each area, converged applications and heterogeneous computing. I think at one point we had about a dozen projects in our portfolio. And I'm going to touch on a couple from each side, a couple of converged application projects and a couple of the heterogeneous computing projects, just to kind of give a flavor. I'm not going to dive into real deep detail on any of those, but I do have PI names listed, and I'm also happy to answer questions or point people into the right direction. One of the interesting things about being kind of the chief scientist of an initiative is I have a high level view of a lot of things, but not a super deep view on any of them. But I'm happy to answer anything that I can. So starting with the converged application thrust area, what are the technical issues or the technical foci that they wanted to address first? So the idea or the objectives are to develop use cases that inform the computing research, including workflows to integrate data-driven methods, as well as physics-driven methods, model-driven methods, domain-aware machine learning, which is a synonym we use for kind of physics-informed machine learning, and traditional computing, particularly as this bullet points out, with strategic interest to the electrical power domain. That expanded kind of as DMC went on into more scientific areas like protein folding and biology and computational catalysis. But we started with an emphasis on the power grid just to kind of have something tractable. So, the two foci that are mentioned here both center around using machine learning methods, either existing machine learning methods or new methods that are developed under DMC's portfolio to enable application-specific advances in computational performance. So improving the performance of existing scientific computing workflows, developing new methods and workflows that integrate machine learning and other data-driven science methods with model-based or physics-informed methods to offer new domain capabilities. So, people have been talking about kind of physics-informed machine learning for some time now for a number of years. But within DMC, when we were spinning up DMC, this was kind of a fairly novel concept. And so, we definitely pushed hard to develop physics-informed learning methods under this project. So I just have a couple of projects here that were in the converged applications portfolio, just to give a brief idea and give more of a flavor than really diving into any sort of deep technical content. But the first one is the exploration of domain-aware machine learning for grid analytics. And the idea here is to utilize domain-aware, unsupervised, as well as semi-supervised machine learning techniques to improve the learning time and reduce the need for labeled data, because often labeled data is sparse. And they looked at two domain areas, the first being information security and the second being kind of energy forecasting. So in information security, the idea is to use unsupervised and semi-supervised learning methods to automate the mapping of common vulnerabilities and exposures to common weaknesses in enumeration. So, if you look at the NIST database, the CVE and CWE common vulnerabilities and exposures, as well as the common weaknesses enumerations databases, there's not a clean mapping from one to the other. So can we use semi-supervised learning to kind of create that mapping that can then be used to, at least mitigate some of the common vulnerabilities that are identified in that database? In the energy forecasting domain, looking at building models for energy prediction, using generative models and integrating those models with physics-informed models to understand how to optimally provide unit commitment and energy costing for dynamic load situations in the power grid. So two interesting areas there. A second project that I'll just touch on briefly is called the holonic approach toward data model convergence. If you ask me exactly how the word holonic relates, I may have to punt. Holonic means something that is itself self-contained as well as part of a larger system. So perhaps you can think about how that relates. But the idea in this project is to use real-time prediction models for cyber physical systems with partial observability. So again, we're talking about the electrical power grid here when we say cyber physical systems. But the approach here is to represent sensor networks distributed across the grid as a dynamic graph with a dynamic topology in which heterogeneous nodes within that graph map to certain cyber physical entities. So those might be power generation units or substations or power transfer devices or things like that. And then to develop domain-aware models for real-time prediction of dynamic systems where we might be able to predict things like cascading failures. So here we might have to, truly integrate the physical models with these data models, where the physical models would capture, how systems fail and under what conditions, and with what sorts of time frames, and then be able to predict in real time for dynamically changing graphs when such a failure may occur and what components within the dynamic graph may get taken down with a failure of any node within that graph. So that's a very challenging problem. And the PI here is Soutine Chowdhury is really driving the adoption of these models on new computing architectures. So he's been working quite a lot with GraphCore and their dynamically reconfigurable data flow systems to understand, can those new architectures provide computing capability that we may not get with a reasonable number of GPUs, for instance. So, if we need 50,000 GPUs in order to be able to provide a real-time prediction, then we probably are going to have problems doing that, since no power company has 50,000 GPU clusters on their premises. So the second thrust area, so in addition to the converged applications, is the heterogeneous computing thrust area. And this is really kind of, if I can say that the converged applications is in the scientific domain space, the heterogeneous computing is kind of in the computer science space. And so it's computer science kind of supporting some of these application domain areas. So within the heterogeneous computing thrust area, there are projects looking at developing hardware, software systems, and tools to support these converged workloads. And how do we adapt hardware software co-design principles and practices to develop system software and hardware architecture concepts. So co-design doesn't have to be hardware software. It could be software or algorithm software. But we've really put kind of an emphasis on the hardware software aspects of co-design. So we have two technical focus areas within this thrust, one looking at system software concepts, one looking at hardware architecture concepts. And I'll just present, I think I have 3 projects that demonstrate these as well. So the first is a compiler tool chain. The project was called Duomo. The compiler is called Comet. And the PI for this is Gulchen Kester. And Comet has been used, developed under DMC, but is starting to be used broadly. She's been having really fruitful conversations with Google and the LLVM and MLIR groups. And so, we're hoping that we can get this compiler used in the community, build up kind of an open source community around it. It is open sourced. If people are interested, I'm happy to share and point you to the right places. But the idea is that the Comet compiler really targets heterogeneous computing infrastructures. So if we have a heterogeneous compute node that has an array of different processor architectures, it could be CPUs, GPUs, specialized accelerators. The Comet compiler can be kind of unifying. Provide a unifying framework that really helps free the software developer from having to think about all these underlying complexities. And so, it utilizes MLIR and others to develop optimized back-end code, whereas her compiler framework really targets front-end compiler optimizations using a tensor algebra, kind of a domain-specific language, which is well suited to a lot of the scientific domains that she's been initially targeting. But we're hoping to with these initial demonstrations under our belt, to broaden this to a wider community. A second project is called SOTA Squared, which is software-defined architectures for data analytics. And Antonino Tomeo is the PI of this project. And SOTA really is kind of a high-level languages to silicon compiler framework, where you might take something in Python or another high-level language and compile down at least a GDS2 down to a silicon description language that can be used with back-end tools from someone like Cadence to actually do place and route and things like that. So, this is an exciting project, and he's demonstrated quite a few successes with his SOTA toolchain, including the SOTA toolchain is actually made up of a few different components, including SOTA Opt, which is kind of the front-end optimizer, and OpenCGRA, which is kind of the back-end toolchain targeting particular CGRA computing platforms. We've also used SOTA outside of DMC, so it also has traction as well in the community and is gaining traction. We've used it with other external sponsors, including DARPA and the other Department of Energy sponsors. So this is a really interesting one as well, and it feeds into the next project, which is called the Compute Flow Architecture Project, or non-von Neumann architectures for data-centric computing. So this one brings together a lot of the concepts that I had described in some of the other projects, where this project really is looking at, if we have large data applications that have huge amounts of data such that moving that data between nodes is a performance bottleneck, what if instead of moving the data, we let the data stay resident and move the computational pipeline kind of over the data using reconfigurable, coarse-grained reconfigurable arrays to have phase-specific architectural implementations that can then operate on the data. So kind of illustrated here on the right is a simple pipeline demonstration or pipeline figure at the bottom, where we're moving these bit files around that describe the computation, which might be kilobytes, as opposed to moving around many tens or hundreds of megabytes or gigabytes rather of data. So it's much more efficient in terms of data movement, much more efficient in terms of the communication performance and overall application performance. So this one kind of brings together SOTA squared, which was the previous slide, because that's the tool chain that's used to define what the architecture looks like on the CGRAs. It brings together the compiler tool chain, because that's kind of the high level first stage in the framework, where the compiler tool chain can interface with the high-level synthesis tool chain through MLIR. They both understand MLIR, so they can come together quickly that way. And so this is kind of a demonstrator of many concepts that are within the DMC initiative. And that one's very exciting, and Ong Lee is the PI of that one. So each one of these projects kind of exists, but we don't want them to exist in a silo, because then we defeat the entire purpose of co-design. And so we had some engagement with the PIs of the individual projects, come together in a co-design, to illustrate our co-design approach. And this slide just points that out as well. Here we bring together the Holonic project, led by Soutine, the CFA project, led by Ong Lee, the SOTA squared project, led by Antonino, as well as a fourth project that I didn't dive into called Fallacy, which is led by Andres Marquez, in order to develop next generation data-centric reconfigurable HPC for domain-aware graph ML applications, targeting a power grid cascading failure challenge problem. So this is kind of really what within DMC we wanted to see, right at the end of the DMC initiative. We wanted to have some of these grassroots co-design collaborations across the projects that we funded within the initiative, so that they could bring their concepts together to solve a large challenge problem. And we achieved some success with that, as demonstrated with this project. I'm almost at the end. I want to save a few minutes for questions, but I wanted to also kind of bring up some advanced architecture testbed concepts that we have within PNNL. We want to be able to demonstrate all these things that we're doing, so we kind of need some hardware to run them on. But clusters with CGRAs and FPGAs aren't quite prevalent. So we stood up a cluster within the past year that we call Junction at PNNL. And it's not a large cluster, it's about 50 nodes, but it's a first of a kind heterogeneous compute architecture. So, at the most basic level, we have two AMD EPYC 32 core CPU sockets per node. And those are connected to two types of accelerators, the AMD M100 Instinct GPU, which is kind of a precursor version of some of the GPUs we find in the exascale computing machines, as well as the Xilinx VCK 5000 Versal ACAP accelerator. And that's, I think, the interesting one. because that one combines programmable logic with hard ARM cores, as well as AI accelerator engines, all in one card. So it itself is a heterogeneous compute node and is part of a heterogeneous compute node that includes CPUs and GPUs. We also have reconfigurable or programmable network cards. The Xilinx Alveo SN1000 card has an FPGA on board. And one of the things that we're doing is exploring how programmable logic at the network interface can be used. So can you do things like data transformations or reductions or collectives, things like that at the network card. And that's kind of an area of ongoing research for us as well. So this system, we've had it for, like I said, about a year. AMD thought it was interesting enough that they decided to build their own 8-node version of it because they didn't have one either, which is actually very helpful because getting these first-of-a-kind kind of systems up and running takes a lot of work. They're never turnkey. And so it's been an ongoing conversation with AMD and Xilinx to get this thing up and running. But I think it's been very worthwhile for sure. So just to conclude, this was kind of a whirlwind, a fire hose dump of what is the DMC initiative. But I wanted to kind of leave the final message that DMC has been a link in a larger chain of PNNL's efforts to build a co-design capability based on expertise in design automation, high-level synthesis at the architectural level, system software, runtime systems, compilers, performance modeling, kind of at the system software level, and how do we bring all these capabilities together to build a unified co-design capability? PNNL's vision really is one of heterogeneity, right? I mentioned this earlier in the talk, but we're not trying to build a better CPU or GPU. That's something I don't think a national lab can succeed at. That's something that is well covered by industry. And so it's not a market that we really want to play in. So we have to think about what is a niche that a national lab can fill and what is our value add to the system design process. And I think a lot of that is we have the scientific expertise, the scientific domain application expertise. And that's something that, is largely unserved directly by industry. We kind of have to pick up where, gaming and other hardware it leaves off. We have to figure out how to use that to do our applications. But what if we could start from scratch, right? What if we had a blank page? How might we do something differently? And how might we integrate with these things that are already in the marketplace and are coming in the marketplace? And so that's what DMC is really trying to achieve. So I think that's all that I had, but I'm happy to take any questions. And I certainly can leave you my email, and I'd love to chat with you over email as well. But thank you.
All right. Thank you so much, Dr. Barker, for this wonderful talk. Is there any questions? I don't see anything in the chat yet. Yes, please, Katie, go ahead.
Yeah, hi, thanks. Something you said earlier about, keeping up with the pace of improvement got me wondering, and I'm guessing the short answer is no, but I'm curious for some applications, is there a point where you might say, okay, we've gotten this good enough? So maybe I'm thinking of something in terms of like processing for a video game or something, where it's like the speed at which it's processing is so fast that it's not going to be noticeable to the user. And so why spend time actually continuing to improve it? Is that something that you discuss ever?
Well, I think that's actually a really interesting question. And I think perhaps in the scientific computing community, it's maybe that might be less true. I think, particularly when you have a human in the loop, like you would with a video game or many other kinds of software, you can get to the point where it's indistinguishable to the human. But I think in the scientific computing world, we typically don't have that. And there's always a push for, I want, my mesh to have more data points. I want to have more physics involved in this simulation, or I want to better understand the boundary conditions between atmosphere and land, or something like that if I'm doing an Earth system simulation. And so I think there seems to be, at least in the scientific computing community, an ever increasing hunger for compute power and memory. Memory has to come with it. And particularly now with data-driven science, memory is much more of a constraint than it used to be. Where it used to be, you could specify the input to a simulation in a simple text file. And now it's like, no, I have, a terabyte of data as well that I need to use to train this model and, so forth. So at least in the scientific world, we haven't seen such a thing. I think one thing, where my brain went when you started asking the question is a lot of the performance improvement that we see, at least at the supercomputer scale, is due to concurrency, right? It's not due to single thread performance. We have seen a lot of application domains that are reaching their limits in terms of concurrency and how much concurrency they can support. So that's one area where I think, we may see computing power leave some applications behind because they just can't. Not many applications can support billion-way concurrency. And when we were doing the exascale computing project, that was a challenge that a lot of the application teams came up with, is how do we use an entire exascale machine, because we just can't support that much concurrency. But I hope that answered your question, at least in a roundabout way.
Yeah, thank you.
Thank you. We have another question from Cameron.
Yes, so my question is about something you said at the end there about how you kind of have to go with what video games have and then run with it. So I'm wondering, is that because video games, right? Of course, they're very common and they're one of the big industry drivers. Are they what most graphics cards and like their software, like their firmware and such, gets, and their drivers get optimized for? And so what you're trying to do is rethink that and maybe make some that are more focused more towards other applications like ML or such.
Yeah, that was the point of my comment, but actually I should probably clarify, because I think that used to be more true than it is now. And I think, machine learning in particular is a large commercial driver. And so we start to see things like GPUs that have mixed precision capability, the tensor core capability that NVIDIA came out with a few years ago. And so it is getting to be the case that GPUs and other industry developed hardware is supporting things like machine learning pretty effectively. I think where we struggle is in the scientific community. The machine learning sometimes has different characteristics of the data. We have a lot of sparsity. GPUs don't like sparsity. And so, we still struggle, I think, with getting, GPUs coming from AMD or NVIDIA or whoever to work well in certain scientific domains. But it's perhaps, I was a little bit oversimplifying the case when I said, oh, we have to take what video game developers want and figure out how to use it. Because I think now machine learning itself is a large application driver, but it still doesn't really satisfy all of the constraints we have in the scientific machine learning community.
Mm-hmm. Yeah, I guess I'm just left wondering what is the difference between using a graphics card? Like what's the fundamental, like what's going on in the graphics card, the difference between what's going on when you're trying to render a scene like for a video game and when you're trying to well, I know what it's going on when you're trying to compute neural networks, because I've been working on them, but I'm just kind of wondering what that fundamental difference is, like firmware wise. I don't think there's really enough time, but very interesting.
Yeah, and I may not be able to give you a very intelligent answer to that question. I know, one of the big things that we struggle with is data sparsity, and having GPUs. You do have GPUs exhibit good performance when the data that they're operating on is sparse. When your tensors are pretty dense, even if your neural network is fully connected, that works well. But in other cases, it's not quite as good, in particular for different types of neural network architectures. But it's an interesting conversation.
Okay, any other questions? All right, I have one last quick question. So for many of these applications these days, the networking and the interconnect choice is now becoming the bottleneck. And I've been wondering, is that part of the DMC? Is there any interesting project going on in that direction?
We do have interesting projects in kind of network design, network topology. It hasn't been as much a part of DMC, but it is something that we are exploring at PNNL. And in fact, one of our government sponsors is very interested in exactly that question, particularly for different types of graph analytics workloads and how they might map to different network topologies. So if you look at things like Dragonfly that exhibit good locality in the network, if you have a problem that doesn't, how do you map it well to a Dragonfly network? And are there other network topologies? We've been exploring some based on Ramanujan networks and so forth. And might those be more suited to these types of graph analytics problems? So it is an important question. It just has not been something that's been in DMC.
Okay, great. Yeah, because it seems like some of this is like for example, there are like a lot of projects now, like trends going into these disaggregated architectures, and
Yes,
the co-design of the whole picture is going to be very interesting and obviously very
yes,
complex.
yes, I completely agree. That is interesting.
Okay, thank you. Any last questions? Or if not, that's it. We all thank Dr. Barker, and thanks for giving us your time. Everybody have a great day.
Thank you for the invitation.
Thank you.
Bye-bye.
Bye.